Have you ever just looked up at the sky and thought about what's really going on up there? I mean, above our heads, there's this invisible chemical war being waged every single day. Countless reactions are happening constantly, changing the very air we breathe. So today, we're going to pull back the curtain, make that invisible war visible, and really dig into the chemistry that's shaping our world. And it all starts with a simple question, right? But the answer, well, that's incredibly complex. Think about it. From the car you drive to work to the electricity that's powering your screen right now, our daily lives are constantly feeding into this atmospheric chemistry. So let's break down exactly what we're putting out there. Okay, so to get on the same page, we need a solid definition. What even is pollution? Well, the word actually comes from Latin pollutus, which literally means to make unclean. And that's exactly what we're talking about here. It's any foreign element, doesn't matter if it's from a volcano or a factory, that makes our air, well, unclean. All right, here's our game plan. We'll start by taking inventory of our chemical sky. Then we're diving into three big consequences: the problem of acid rain, the global greenhouse, and the hole in our shield. And we'll wrap up by looking at some pathways to protection. So let's kick things off. Before we can really get into the problems, we've got to meet the players, right? Who are these chemical culprits that are changing our atmosphere? This table lays it out pretty clearly. Now, yeah, nature does its part. You see things like volcanic eruptions, but what we're really zoning in on are the man-made sources. And I want you to pay close attention to two of these: the oxides of sulfur and the oxides of nitrogen. They come from burning fossil fuels and from our cars. Definitely keep those two in mind because they are the main characters in our first big story. And that first big problem is acid rain. Yep, this is exactly what happens when those pollutants we just flagged, those oxides, get up into the air and mix with water. The result is rain that can literally be corrosive. Okay, this diagram might look a little complex, but the basic idea is super simple. You've got factories and cars pumping out sulfur dioxide and nitrogen oxides. These gases rise up into the atmosphere, they mix and react with the water up there, and then they come back down. And it's not just as rain, it can be snow, fog, or even as dry particles. It's called acid deposition for a reason. So let's get into the nitty-gritty of the chemistry. If we just follow the sulfur, for example, it starts as sulfur dioxide, or SO2. Up in the air, it gets oxidized and becomes sulfur trioxide, SO3. Then that stuff reacts with water vapor, and bam, you get sulfuric acid. A very similar thing happens with nitrogen oxides, which creates nitric acid. It's this simple but incredibly destructive chain reaction. So, how acidic are we really talking here? Let's look at the pH scale. Now remember how this works. It's not a straight line. Every single number you go down, it's 10 times more acidic. So pure water is a neutral 7. Normal rain, believe it or not, is already a little acidic, around 5.6. But acid rain? It can drop to a pH of 4 or even 3.5. That means it can be almost 100 times more acidic than regular rain. That is a massive difference. And what does all that acidity do? Well, for one, it literally eats away at our history. It corrodes buildings and priceless statues, especially those made from limestone or marble. It also gets into our soil and completely changes its chemistry. The acid rain basically washes away essential nutrients, things like potassium and calcium that plants need to grow. This makes the soil way less fertile. And of course, it ends up in our lakes and rivers. And the impact there is just devastating. A lot of fish and other aquatic creatures can only live in a very specific pH range. Once a lake's pH drops below 6, things start to die. A fish like salmon, for example, just can't survive if the pH dips below 5.5. Okay, let's switch gears to our second major challenge, the greenhouse effect. If you think of acid rain as a problem of chemical corrosion, this one is all about trapping heat, basically giving the entire planet a rising fever. So here's how it works, and it's actually pretty simple. The sun's energy comes in and warms up the Earth. The Earth then tries to radiate some of that heat back out into space. But certain gases in our atmosphere act like a blanket, and they trap some of that outgoing heat. Now, a little bit of this blanket is good. It's what keeps our planet from being a frozen rock. But the problem is we're making the blanket thicker and thicker, and that's leading to overheating. So what's this thicker blanket made of? Well, the main culprit, no surprise, is carbon dioxide. It's responsible for about 55% of the warming, But it's not alone. Methane and CFCs are also big players. So it's important to remember that even though we often just say carbon emissions, it's actually a cocktail of different gases that are making up this warming blanket. And where is all this stuff coming from? This chart is a real eye-opener. Look at that. Transportation is the absolute giant here, making up more than half of the emissions. After that, you've got electricity and agriculture. This really paints a clear picture of which parts of our lives have the biggest footprint. And the consequences of all this warming? They're global, and they're serious. It's like a massive chain reaction. Ice caps melt, which makes sea levels rise, which then threatens coastal cities. At the same time, weather patterns get thrown out of whack, ecosystems are disrupted, and even the fertility of our soil can change. It's all connected. All right, on to our third and final problem, the ozone layer. So, if the greenhouse gases are a blanket, the ozone layer is like Earth's critical high-tech sunscreen. And for a while there, we were poking some serious holes in it. So what is it exactly? It's basically this thin layer of ozone molecules way, way up in the stratosphere. And its job is absolutely critical. It blocks about 98% of the sun's most harmful ultraviolet radiation. Let me be clear, without that shield, life as we know it on the surface of the Earth would be pretty much impossible. So how does this natural sunscreen work? It's actually a really elegant cycle. The same UV light from the sun is constantly creating new ozone and also breaking down old ozone. In a healthy sky, it's a perfect balancing act. The amount of ozone being made is the same as the amount being destroyed, so the shield stays strong and stable. But then, we came along and introduced chemicals called chlorofluorocarbons, or CFCs. And at the time, they seemed like a miracle. They were non-toxic, super stable, and great for things like aerosol cans and refrigerators. But that very stability was the hidden danger. They drift all the way up to the stratosphere, where the UV light finally breaks them apart and releases a chlorine atom. And here's the absolutely crazy part. A single one of those chlorine atoms can set off a chain reaction that destroys over 100,000 ozone molecules. It just completely wrecks that delicate natural balance. So what happens when the shield gets thinner? More of that harmful UVB radiation makes it to the surface. For humans, that means a higher risk of things like skin cancer and cataracts. But it's so much bigger than just us. That extra UV radiation stuns the growth of plants, the base of pretty much every food web. And that causes disruptions that ripple through entire ecosystems. Okay, wow. We've just laid out 3 really serious problems with our atmosphere. So what's the solution? What's the prescription? Let's move into our final section and talk about some pathways to protection. And this is where things get complicated. We have some amazing potential solutions. Solar, wind, hydropower. These are all ways to get energy without producing the nasty pollutants we've been talking about. But, and this is a big but, each one has its own major challenge. Hydropower dams are incredibly expensive to build. You need really steady, strong winds for wind power to be reliable, and collecting and converting solar energy efficiently is still a huge hurdle. The takeaway here is that there are no simple magic bullet fixes. Which leaves us with one last really big question to chew on. Think about it. Acid rain, global warming, ozone depletion, they all come from the same place, right? They're all byproducts of our modern industrial world. They're all interconnected. So if they share a common cause, is it possible they also share a single solution? Do we need to look for one systemic change that tackles the root cause of all of them? Now that is something to think about.